This video introduces the R-Shiny apps that run dynamic energy budget model simulations. These dynamic energy budget models are a really powerful way to predict organisms' trajectories of growth and reproduction under variable environments. It's based on a theory of metabolism, the dynamic energy budget theory, and it connects beautifully with the biophysical models to create a complete perspective on how environmental conditions affect species' ability to develop, grow, survive, and reproduce in a given location. These apps just run the dynamic energy budget model on its own without integrating with the biophysical models, but that can be done using the ectotherm function in the niche mapper package, and subsequent apps will actually allow this, but they're yet to be constructed. So this is the web app for the dynamic energy budget model. There are actually two. This one is for constant environmental conditions. And by default, it's running a simulation of the species for which dynamic energy budget theory was first invented, Daphnia magna. So I've got some pictures of Daphnia magna on the banner at the top. And what you can see in this plot, this colored plot, is the trajectory of wet mass of the Daphnia growing at 20 degrees under constant food. So what this graph is showing is the wet mass decomposed into different components that represent the state variables in the Deb theory, or some of the state variables in the Deb theory. So in green, you have the structure of the organism. This is the part of the biomass that requires maintenance and is the organized part of the biomass. The grey is the reserve, which is the metabolic substrate that food gets converted into and then gets mobilized to run the metabolism. The brown is the food in the stomach of the Daphnia, and the pink is the reproductive buffer. It's the energy that's been put into making eggs, and you can see the sawtooth pattern is due to the fact that the eggs are being dispensed to the environment once the organism has enough reproductive buffer to produce a clutch. The controls are on the left-hand side, and you can see that the temperature is set to 20 degrees. It's running for 50 days on an hourly time step. The clutch size is 5 eggs. It's starting off as an egg, and you can control the dimensions, or the units, sorry, for the plots. So it's using milligrams for mass, and you also have a series of other plots. There's a plot of respiration as a function of mass. There's a breakdown of the different energy fluxes into the different processes, metabolic processes that the Deb theory is covering. There's the growth in length here as millimeters through time, and a number of other things which I'll go through in a second. But let me first just go through the Deb model a little bit more, looking at this diagram here. So the Deb model starts off as an egg and goes through the whole life cycle, the process of hatching and then feeding. So in the Deb theory, birth is actually when the organism first starts feeding. Puberty is when the organism has become mature and then starts allocating energy to reproduction. So you can see those time points in the life cycle represented by these vertical dashed lines. So I've run the simulation for 50 days. If I run it for just 2 days, we'll get to look in close up at the first part of the life cycle when it starts off as an egg. And you can see that right at the start, the animal is composed of almost entirely by a reserve. So the freshly laid egg is essentially pure reserve. Reserve is not just fat, it's all the things you need to make a baby Daphnia or a baby chicken or whatever the organism is. It's lipids and proteins and carbohydrates, polymers that are mobilized and then used to run the metabolism, including build the organism as well as maintain it. So you can see that the mass is going down at the start because the reserve is being used and respiration's happening, and some biomass is being lost, some carbon's being lost, nitrogenous waste is being lost. But you can see the structure in the green, which is the little embryo developing, is going up. And then we get to a point of birth where you start to see this brown color appearing, and that's the organism starting to feed. So now it starts increasing in mass because it's taking in mass, as opposed to when it's an egg where it's just consuming the yolk. And you can see in the plot of metabolic rate versus mass that you've got this funny thing going on where it starts off at a high mass and metabolic rate is virtually zero, because there's no structure yet to maintain. And then the metabolic rate goes up as the structure is growing and the size is going down. So the metabolic rate rises, the size goes down, and then it hatches, and then metabolic rate starts going up with size. So if we go back to a 50-day simulation, we were just looking at really close at that section there, but now you can see the metabolic rate is doing what you would expect. It's rising with body mass with a power function. If you characterize it as a power function with an exponent of roughly 3/4. So that part is just coming out of the stoichiometry of the DEB model. The DEB model assumes a certain composition of the reserve and the structure, the food and the feces, and it does a full stoichiometric balance based on that, which gives you the metabolic rate in terms of the heat production and also the oxygen flux, and outcomes the scaling, in this particular case around about 3/4. If we look at the plots of the energy fluxes to the different processes, you can see all the different processes that are occurring in the dynamic energy budget model. We have the process of assimilation, which is food being converted into reserve, a chemical transformation. We have the process of reproduction, which is when the reserve is being converted into material, into reproductive tissue, which initially may be just earmarked for reproduction, but ultimately it may be stored in the liver or something like that, but ultimately drawn down on to produce the eggs when the animal's in the season for reproduction. With the DEB theory, it's set up with something called the Kappa rule, where the flow of resources, energy and materials out of the reserve is split, and a certain fraction, which is dictated by the parameter Kappa, say 80%, goes to growth and maintenance, and the remainder goes to initially the process of maturation and subsequently the process of reproduction plus maintaining maturation. So the green here, sorry if you're red-green colorblind, but this is green here, is the process of maturation, which is happening from birth all the way through to puberty. The maturity level is going up. Energy is actually being spent on making the organism more organized, more complex. And then once it reaches a certain threshold of maturity, it becomes mature and starts allocating to reproduction, but continues to allocate energy to maintain the level of maturity it reached. So you can see that it starts off with no red, just the green, and then at maturation, you can see that the maintenance of maturity continues, but some of that flow that was going down that path of 1 minus Kappa is going to reproduction. Then you can see in yellow the allocation to growth, which you can see is becoming less and less as the organism becomes bigger. And in blue, you can see the allocation to maintenance. And the allocation to maintenance is going up in direct proportion to this structure, the green here. And the growth tapers off because the intake, the assimilation process, is happening in proportion to the structure, to the power of 2/3, to the surface of the area of the structure. And so with the maintenance going up in direct proportion to the structure, eventually maintenance takes everything because the maintenance rate's going up faster than the assimilation rate, and that's what causes the growth to asymptote, and you get this von Bertalanffy shaped growth curve that you can see in this figure here. I've also included a plot of the scaling of reproduction with mass, just because that's of theoretical interest for many people. So this is showing a prediction of a scaling of 0.9 of reproduction with mass. And if we go down a bit further, you can see the parameters of the dynamic energy budget model that were pulled out for the Daphnia. So there are a series of parameters, one for each process. So we have a parameter for the feeding conversion efficiency, which is generally speaking left by default, something like 0.8 or 0.9. We've got the assimilation parameter. We've got the maintenance parameter, a parameter for the maintenance of maturity, energy conductance parameter, which is dictating in part how fast the reserves flow out of the reserve pool, the maximum reserve density, the cost of growth, the allocation fraction I mentioned. So in the Daphnia, 58% is going to growth and maintenance, and the remainder goes to maturation and then reproduction. The efficiency of reproduction, which is generally by default assumed to be a conversion efficiency of about 0.95, because it's just converting the reserve into eggs, which is very similar biochemically. And then these thresholds of energy invested at the point of birth, metamorphosis, if the species metamorphoses, this Daphnia doesn't, at the time of maturity. And then we've got the parameters for the thermal response, and this is the 5-parameter Arrhenius response. But the most important one here is the Arrhenius temperature there, which is the parallel to the Q10, if you're more familiar with Q10s. And then these plots, these 6 plots, show the fluxes of what are called the minerals in the Deb theory as a function of age rather than mass. So we've got the oxygen consumption rate, the carbon dioxide production rate, the metabolic water production rate, nitrogenous waste production, and then it's also got the dry food intake and the wet feces output out of interest. So these are all the things that this app plots, and you can choose any species that's in the collection of Deb parameters that's available on the Add My Pet website. And that website, you can see on this next page, there are, as of today, 4,007 entries in the collection of all different taxa. You can see the range of taxa here. So there's mostly vertebrates, but we do have some insects in there as well, and other invertebrates. There's a whole lot of information on this page about the dynamic energy budget theory. So if you're interested to learn more about the theory, have a look at this page. And if you want to see what's in the collection, you can go to this collection tab. You can see all sorts of information about the collection, but the species list will show you all the species in the collection, and you can search by phylum, class, order, or family, or species, or common name. And there are also different models of the Deb theory. I mentioned metamorphosis. There is a model where organisms accelerate in growth up to a point of metamorphosis. So that's one of the different sorts of models. There are different models for insects and for holometabolous insects versus hemimetabolous insects. So there are quite a few different sorts of models, and this app that I've made doesn't, and the actual niche map and Deb functions don't accommodate all of those, but they do accommodate many of them. Okay, so if we wanted to do a different species, let's just say we wanted to look at the Atlantic cod. So this is Gadus morua. If we run the simulation, we're going to get a calculation of the trajectory of the Atlantic cod, but we've got it for 50 days with an hourly time step at 20 degrees. And so you can see we've got the egg development. It took about 9 days to develop, and then it actually does have an acceleration phase, and then it metamorphoses at about 28 days or 27 days, and then the growth slows down to a normal von Bertalanffy pattern. But of course, this fish has only gotten to 600 or 60 grams. I mean, 6 grams, I should say, or just over 6 grams by the end of 50 days. We want to run a longer simulation. So let's make it go for 10 years. We'll make it a daily time step and keep it at 20 degrees and run the simulation. Okay, and we can see that it's starting to reproduce. Hasn't reached the maximum size, but if we make the temperature higher, then it will grow faster. You can see it's starting to reach an asymptotic maximum size. We should probably put the mass in kilograms. So now it's getting up to almost 150 kilograms. We've got a clutch size of 5. Let's make it 1 million. And then we'll see that it's you can't really see very well, but there's this more sawtooth pattern to the reproduction here. Because before it was only having a clutch size of 5 and the buffer kept filling up and wasn't emptying as fast as it was filling up. If we make it add another 0 there, we'll end up with a more obvious periodic reproduction. Okay, so that's the Arctic cod developing at constant temperature and constant food. If you want, I've also got a couple of other options to play around with parameters of the Deb theory. So there's this multiplier on the size. In the Deb theory, there's an expectation for how different aspects of the organism's metabolism will scale with size, all else being equal, as a kind of a null expectation from a purely physical point of view. This comes from the treatment of parameters as either intensive or extensive parameters. These are physical concepts. Parameters like concentration, temperature are intensive, have an intensity, whereas extensive parameters relate to the size. And if you assume by default that all the extensive parameters change together, and in the Deb theory, that includes the parameter dictating the energy invested at birth, in maturity by birth, in maturity by puberty. And so when you increase the size, you expect the size at birth, the size at puberty, and the maximum size to all change together, and by default, unless there's stabilizing selection, for instance, on the size of the hatchling. And the egg also therefore scales with size as well. So if we make this a larger cod, we'll get an increase in the size at puberty, the size at birth, and the maximum size, all of those things together. So you can have a look at what you would expect to happen with the evolution of larger or smaller sizes using this slider, just using the Deb theory covariation rules, they're called. You can also play around with one of the parameters, which people often find quite interesting, the Kappa parameter, and change the allocation fraction. So if we make Kappa larger, what you should see, actually, you've got to be careful with some of these, because going too far will cause physically impossible situations, and so the model won't run. Anyway, those are some of the things you can play around with. You can also turn the aging off or on. So at this point, I've run the Daphnia this is back to the default Daphnia. I ran the Daphnia for 50 days, but it has an aging module that's a temperature sensitive module, and it died before it got to 50 days. If I turn that off and run the simulation, you'll see it goes all the way out to 50 days. So you can just see what would happen if the animal was living longer than the parameters of the model would dictate. And you can also turn off this, you can exclude the egg stage out of the respiration exponent calculation. So if I click on that and I have to hit run again, you'll get the scaling of metabolic rate with size through ontogeny that doesn't include the egg stage. Okay, so that's the standard app for the Deb theory. If we go back to the tools, there's one other app on Deb theory called the Dynamic Energy Budget Model in the Sea. So this app allows for fluctuating temperature and food. So it's only for using sea surface temperature. So I've got it connected to a database of sea surface temperatures. So it's really only relevant to species that are living in the water, although you can choose any species you like and run it. So we've got the cod, the Atlantic cod here simulated. You can choose in this app where you want to run the simulation. So it will draw the sea surface temperatures for that location. So we're out in the North Atlantic Sea, and you can see the temperature from the sea surface temperature here, and it's historical. So it's the starting time you can choose from a range of starting times going back to 1981. So this is starting in 1981, and it shows you the annual sea surface temperature pattern here in this particular part of the world. And then you can see the growth of the Atlantic cod as a function of those thermal conditions. So you can see that there's a seasonal pattern to the growth, seasonal pattern to the oxygen consumption, and all the other fluxes. And the growth in length is looking a bit more wobbly because of the temperature effects, and the reproduction function looks a little bit different as well if you were to fit a line through that. So this is a way to explore how variation in environment might affect the trajectories that you see. It's otherwise similar to the previous interface in that you can control at what stage the animal starts in its life cycle, egg, hatching, puberty, or adult. You can control the clutch size, how it's expressing the dimensions, and these other controls down here. You can also get the output, by the way, by clicking on the Save Output. You'll get a CSV file with all the values that are being plotted, plus a few more. We can go to a constant temperature just to compare. So what we had before was, well, now is a cycling temperature between about 14 and about 7. So if we just make it, say, 11 degrees constant and run the simulation, you can see what would have happened for comparison. Turn that off. We can also play around with the food in a certain way. So if we click on the Show Food Parameters, a number of other parameters pop up. There are 6 more things you can change. I won't go into exactly how the Deb feeding model works, but it's using a type 2 functional response with a half saturation constant. You've got the maximum and minimum food density that you can choose. You can play around with the multiplier on the intake rate. This is PXM, this is the intake rate. And you can also specify how big the stomach is. So this is expressed as joules per centimeter cubed of the structure, which is this green. Remember, the structure is the green section there. So you can make the stomach larger or smaller. If I make it have a really huge stomach and run the simulation again, you'll see this brown area should get larger because it's got a bigger stomach. But then you can play around with the pattern of the food. So you can have a constant amount of food, and we can alter that. Actually, the F is controlling the overall mean amount of food. So if I make it 0.8, you will see, so it grew to about 15 kilos in this simulation with F is 1, which means ad libitum food. F is 0.8 should make it not grow as large. So 8 kilograms in that time. And we go back to making it 1, but we can also change the pattern seasonally. So we can say it's either constant or it has a pattern where, help for this is not coming up well, but where there's a peak at the solstice or a peak at the equinox, depending on what's going on for your species. There might be algal blooms, for instance, in the summer, or there might be in spring. So if we take the equinox pattern of food availability, run the simulation, you'll see this will change to show fluctuating food. And the growth trajectory has changed as a result, as everything else. So this allows you to explore the consequences of fluctuating food and temperature on the trajectories of growth. The powerful thing about the Deb theory and about biophysical models in general is you can provide these somewhat simple models with very complex sequences of environmental conditions like these, and you can see how the growth trajectory, reproduction trajectory, and so on respond. And this allows you to make predictions of how species will respond to complex environments.